The universe you learned about in school was the wrong size. Not slightly wrong. Not off by a comfortable margin. Wrong by a factor of 7. For most of modern astronomy, scientists calculated the size of the observable universe by multiplying the speed of light by the age of the cosmos. The math is simple enough. Light travels at about 300,000 kilometers per second. The universe is 13.8 billion years old, so the observable radius should be 13.8 billion light-years in every direction. Clean and logical, except the actual edge of the observable universe sits 46.5 billion light-years away. The full diameter measures 93 billion light-years across. We live inside a sphere of visible space nearly 7 times wider than simple arithmetic would predict. That is not a rounding error. It is a fundamental property of reality that upends naive intuitions about how space and time behave. Before we continue, if this kind of content sparks your curiosity, subscribe, because the deeper we go, the more surprising it gets, and most people never hear about what you're about to see next. The James Webb Space Telescope, positioned 1 million miles from Earth, has been systematically probing the depths of that sphere since late 2021. What it found was not a gradual confirmation of existing theories. It was a cascade of surprises, each one nudging the foundations of cosmology in ways researchers are still working to understand. The telescope has seen galaxies that should not have been massive enough to exist yet. It has detected chemical fingerprints left by types of stars that had never been directly observed. It has counted galaxies in patches of sky that Hubble photographed for decades and found 80 times more objects hiding in the same darkness. To grasp why any of this matters, you first have to understand something about the nature of light itself. Every photon that has ever entered your eye left its source sometime in the past. When you look at a candle across a room, you are seeing the flame as it appeared a few billionths of a second ago. Look at the moon, and you see it as it was 1.3 seconds earlier. The sun appears to you as it existed 8 minutes ago. The nearest star system, Alpha Centauri, shows itself as it looked 4 years back. The Andromeda Galaxy, the largest structure you can see with your naked eye on a dark night, appears to you as it existed 2.5 million years ago, before our genus Homo had evolved. This is not a metaphor or an approximation. It is the literal structure of observation across a universe where light travels at a finite speed. When astronomers point telescopes at distant objects, they are not merely looking far away. They're conducting archaeology on time itself, excavating layers of the past at different cosmic depths. The James Webb Space Telescope is the most powerful instrument ever built for this kind of excavation. Its primary mirror spans 6.5 meters and is coated in gold, not for aesthetic reasons, but because gold reflects infrared light with exceptional efficiency. Infrared is the key. The most distant galaxies in the observable universe emitted their light billions of years ago as visible or ultraviolet radiation, but the expansion of space has been stretching those wavelengths ever since. By the time ancient photons reach Webb's detectors after traveling for 13 billion years, they have been stretched far into the infrared range, invisible to human eyes and to most previous telescopes. Webb was built to see exactly this stretched, ancient light. The most distant confirmed galaxy Webb has detected is designated JD's GS Z14-0. When scientists first spotted it in October of 2023, they spent months questioning what they were seeing. The object appeared too bright, too large, too developed. When Webb's spectrograph analyzed its light in January of 2024, the measurement was confirmed. This galaxy sits 13.5 billion light-years away and emitted the light Webb collected when the universe was only 290 million years old. 290 million years sounds like a long time. In cosmic terms, it is nothing. The universe is 13.8 billion years old. This galaxy formed when the cosmos had existed for just 2% of its current age. If you compressed all of cosmic history into a single year beginning on January 1st, JD's GS Z14-0 formed on January 2nd. What stunned researchers was not just the distance. It was what the galaxy contained. The object measures over 1,600 light-years across and holds several hundred million times the mass of our Sun, all packed into young stellar populations blazing with ultraviolet light. Theoretical models had predicted that galaxies at this cosmic age would be small, dim, and structurally simple, a collection of perhaps a few million stars at most. The universe at 290 million years old was not supposed to have had enough time to build anything resembling what Webb found. Gravity is patient, but not infinitely fast. Gas clouds need time to cool before collapsing. Dark matter halos require time to accumulate mass before they can anchor galaxy formation. Stars need millions of years to form, live, and die. Each step in the chain has a minimum duration set by physics. The standard model of structure formation calculates precisely how much material can pile up into a galaxy at any given age. JDES GS-Z14-0 exceeded those expectations by a considerable margin. The team also found something in the galaxy's spectral signature that compounded the mystery. Alongside hydrogen and helium, the light contained the unmistakable fingerprints of heavier elements: carbon, oxygen, nitrogen. These atoms do not form in the immediate aftermath of the Big Bang. They are forged in stellar interiors over millions of years and then dispersed through space when those stars die in supernova explosions. Their presence in a galaxy 290 million years old means an entire generation of stars had already lived and died before this galaxy formed. The cosmic timeline keeps being pushed backward. One astronomer compared discovering JDES GS-Z14-0 to excavating a smartphone among Roman ruins. The object is too sophisticated for when it appears, the structure too developed, the chemistry too advanced, the brightness too intense for the era in which it exists. Webb also found a second galaxy nearly as distant in the same field of view, designated JDES GS-Z13-1, two record-breaking galaxies in the same small patch of sky, both contradicting standard models, both producing starlight at rates that existing theory cannot fully account for. That statistical coincidence is itself a signal. If galaxies this extreme cluster in one surveyed area, they are not rare exceptions. They are representatives of a widespread population that pervades the early universe. Now take the problem of these individual galaxies and scale it up. Webb stared at a region of sky slightly larger than 3 full moons for 250 hours, collecting photons from the faintest sources it could detect. Scientists call this region the Cosmos Webb Field. When the Hubble Space Telescope examined the same area over years of observation, it found roughly 10,000 galaxies. That seemed comprehensive. Researchers believed they had counted most of what was there. Webb found 797,942 galaxies in that same field, nearly 800,000 distinct collections of stars where Hubble had cataloged 10,000. Not because Hubble miscounted the galaxies it could see, because vast populations of galaxies were completely invisible to it, hidden in wavelengths of light its instruments could not detect, revealed only by Webb's infrared sensitivity. The image required combining more than 10,000 individual exposures, each carefully aligned and corrected for observational artifacts. To understand the visual scale of this result, if you printed the Hubble Ultra Deep Field on a standard sheet of paper at full resolution, printing the Webb Cosmos Field at equivalent detail would require a panel 13 feet tall by 13 feet wide, a mural of cosmic history covering an entire wall, every point of light in it a galaxy, each galaxy containing hundreds of billions of stars, each star potentially orbited by worlds. What this galaxy count means for our understanding of the cosmos is still being worked out. Before Webb launched, astronomers estimated the observable universe contains roughly 200 billion galaxies. That number came from Hubble surveys. Count galaxies in a small patch, extrapolate to the full sky, account for the regions too faint to detect. The method seemed sound. Multiple independent surveys agreed. Webb's deep field observations suggest the true count could be trillions, not hundreds of billions. Trillions. If each of those trillions of galaxies contains a quantity of stars comparable to the Milky Way's 200 billion, and if each star hosts on average even one planet, the number of worlds in the observable universe alone becomes so large it defies any useful intuition. For every grain of sand on every beach on Earth, there may be 100 planets out there in the dark, but counting galaxies is only the beginning of what Webb has upended. Before examining what Webb found in the structure of those galaxies, it is worth pausing on the physics that makes the 93 billion light-year diameter of the observable universe possible in the first place, because this is where intuition fails completely. Common sense says, the universe is 13.8 billion years old, light travels at a fixed speed, therefore nothing can be farther than 13.8 billion light-years from us. This reasoning is wrong because it treats space as a static container. Space is not static. It expands. Imagine drawing dots on a rubber balloon, then inflating the balloon. The dots separate from one another, not because they are moving across the balloon's surface, but because the surface itself is stretching. The dots are not moving through space. Space is growing between them. Galaxies in the real universe behave the same way. They do not travel through space like ships through water. Space carries them apart. When a galaxy 13.5 billion light-years away emitted the light Webb collected, it was not 13.5 billion light-years from us. It was much closer. But during the entire time that light was traveling toward us, the universe was expanding. The galaxy moved farther and farther away while its light was still in transit. By the time those ancient photons finally arrived at Webb's detectors, the galaxy that emitted them had been carried to a current distance of about 46 billion light-years. The light reached us, but its source has receded to a position far beyond where it started. Think of it like running towards someone on a treadmill that is slowly speeding up. You might eventually reach them, but they will be considerably farther from where they stood when you began. Light does the same thing, constantly moving toward us at the speed of light, but the space it is crossing keeps growing. This explains the 93 billion light-year diameter. The observable universe is not defined by how far light can travel in the universe's lifetime. It is defined by how far light can reach us given that the space it crosses has been expanding the entire time. The result is a sphere roughly 7 times larger than naive calculation would suggest. Now add one more layer of strangeness. Regions exist beyond 46.5 billion light-years that are part of the universe. We know they are there. The observable universe shows no signs of an edge or boundary. Galaxy distributions look statistically similar in all directions. The cosmic microwave background is nearly uniform across the entire sky. All of this points toward a universe that continues beyond what we can see. It just continues into regions from which no light has had time to reach us yet, and the situation is not improving. Dark energy, the mysterious force driving cosmic expansion, is causing that expansion to accelerate. Distant galaxies are receding from us faster over time, not slower. Eventually, galaxies that are currently inside our observable sphere will cross the horizon and disappear. Their light will be stretched into such extreme wavelengths that it becomes undetectable, and then they will recede faster than light can bridge the widening gap between us. Scientists calculate that in approximately 150 billion years, every galaxy outside our local gravitationally bound group will have vanished beyond the cosmic horizon. Future observers in the Milky Way will see only their immediate neighborhood, a few dozen galaxies. They will have no way of knowing that billions of others once filled the sky. The evidence will have raced away into permanent darkness. We live in an era of unusual cosmic visibility. We can see 13.8 billion years of history in every direction. That window is slowly closing. Dark energy comprises 68% of everything that exists. Not dark matter, not ordinary matter, not radiation. Dark energy, a component of the universe whose physical nature remains genuinely unknown despite being its dominant constituent. It was discovered in 1998 when 2 independent teams of astronomers were measuring the brightnesses of distant Type Ia supernovae, stellar explosions whose intrinsic luminosity is well calibrated. By comparing how bright these supernovae appeared against how bright they actually are, researchers calculated their distances. When they plotted those distances against how fast the supernovae were receding, the data returned an impossible result. Expansion was not slowing down. It was speeding up. The supernovae were farther away than they should have been if the universe had been decelerating under gravity's pull. Something was pushing space apart at an increasing rate. That something is dark energy. Its defining property is deeply strange. Unlike matter and radiation, which dilute as the universe expands, dark energy's density remains constant. If you double the volume of space, you double the total amount of dark energy. This means dark energy becomes progressively more dominant as the universe grows. Early in cosmic history, matter and radiation controlled the dynamics. Gravity-shaped structure. About 5 billion years ago, dark energy's total influence overtook matters and became the primary driver of cosmic evolution. That transition is still ongoing. Dark energy is not done reshaping the universe. The specific value that describes dark energy's behavior, called the equation of state parameter, appears to be close to -1. This corresponds to what physicists call a cosmological constant, a term Einstein originally introduced into his field equations to allow for a static universe. He later called it his greatest mistake after Hubble's observation showed the universe was expanding. It turns out Einstein's mistake was accidentally describing something real. Dark energy behaves, at least approximately, like a constant energy density built into the fabric of space itself. Whether it truly is constant, or whether its strength changes subtly over cosmic time, is one of the central open questions in physics. Small deviations from constant behavior would imply entirely new physics beyond the standard model. Webb's observations are contributing to answering this question by mapping how the universe's expansion rate has varied across different cosmic epochs, and those observations have revealed something troubling about our measurements of that rate. The expansion rate of the universe is described by a number called the Hubble constant. Two different methods for measuring this number are producing two different answers, and the discrepancy will not go away. The first method analyzes the cosmic microwave background, the faint afterglow of radiation left over from 380,000 years after the Big Bang. This radiation contains a pattern of tiny temperature variations that encodes information about the universe's composition and geometry at that early moment. By fitting the standard cosmological model to this pattern, scientists extract a value for the expansion rate today. The result is approximately 67 kilometers per second per megaparsec. That means for every megaparsec of distance, roughly 3.2 million light-years. Galaxies recede from us at an additional 67 kilometers per second. The second method measures the expansion rate directly in the nearby universe using objects of known intrinsic brightness. Cepheid variable stars pulse at rates directly linked to their luminosity, allowing astronomers to calculate their distances. Type Ia supernovae provide a similar calibrated brightness. By combining these distance measurements with the recession velocities of their host galaxies, scientists measure the local expansion rate. That measurement consistently returns approximately 73 kilometers per second per megaparsec. The gap between 67 and 73 might seem minor in the context of cosmological measurements, but it is statistically significant at a level that rules out coincidence. Both measurements have been independently verified dozens of times using different instruments, different calibration methods, and different statistical approaches. Webb confirmed the local measurement using the largest sample of Cepheid and supernova data ever compiled during its first 2 years of operation. 3 separate distance measuring techniques agreed with each other and with Hubble Space Telescope results. The systematic errors Webb's critics suggested might explain the tension are not there. This means either the early universe prediction is wrong, the late universe measurement is wrong in a way nobody has identified, or the standard cosmological model is missing physics that caused the universe to evolve differently between early and late epochs. Each of those possibilities is scientifically significant. The third possibility is especially intriguing because it implies something genuinely new, unknown particles, unknown fields, or dark energy that is not constant but has been changing in strength over cosmic time. The Hubble tension is not going to be resolved by better measurements alone. It may require better physics. At the centers of the most distant galaxies Webb has observed, something even harder to explain than galaxy formation itself is present: supermassive black holes. Objects containing millions or billions of times the mass of our Sun, existing when the universe was only a few 100 million years old, in structures that should not have had nearly enough time to grow them. Galaxy GNZ11 provides the clearest case. It is one of the most distant galaxies ever spectroscopically confirmed, existing when the universe was only 430 million years old. Nested at its center is a supermassive black hole whose mass is estimated at millions to possibly billions of solar masses. Webb detected the signature of extremely dense gas spiraling inward, a clear indicator of rapid accretion. The black hole was actively feeding at the time this light was emitted. Standard stellar evolution produces black holes through a specific path. A star must be at least 20 times more massive than our Sun to end its life as a black hole rather than a neutron star or white dwarf. When such a star exhausts its fuel and collapses, The resulting black hole typically weighs 10 to 100 solar masses. Growth from there requires pulling in additional material through accretion, a process governed by a fundamental physical limit called the Eddington rate. The Eddington limit describes the maximum rate at which a black hole can consume matter before the radiation pressure from its own heat pushes infalling gas outward and shuts down accretion. Even consuming matter continuously at the maximum possible rate from the moment after the Big Bang, a black hole formed from a collapsing star cannot accumulate billions of solar masses by 430 million years into cosmic history. The physics simply does not allow it, yet GNZ11's black hole exists. And GNZ11 is not unique. Webb has found multiple supermassive black holes in the early universe, some appearing even more massive than expected for their cosmic age. Each discovery deepens the same puzzle without resolving it. Several theoretical mechanisms have been proposed to explain early supermassive black hole formation. The first involves what cosmologists call direct collapse black holes. In the dense early universe, under specific conditions, a gas cloud containing the equivalent mass of 100,000 or more suns might bypass the star formation process entirely and collapse directly into a black hole of equivalent mass. No stars form, no stellar evolution plays out, no waiting millions of years for a massive star to live and die. The cloud becomes a black hole in a single gravitational event. Mathematical models show this is theoretically possible under conditions that may have existed in the early universe. Nobody has directly observed it. A second proposal involves dark stars, theoretical objects powered not by nuclear fusion, but by dark matter annihilation. If dark matter particles collide and annihilate each other inside a massive gas cloud, they generate heat that supports the cloud against gravitational collapse, much like nuclear fusion supports ordinary stars. These dark matter-powered objects could potentially grow to millions of solar masses before the dark matter supply diminishes and the cloud collapses directly into a correspondingly massive black hole. This would give early black holes a massive head start on growth. Dark stars remain entirely theoretical, supported by mathematical arguments, but not yet by direct observation. A third mechanism involves elevated merger rates. The early universe was denser and more chaotic. Galaxies were closer together. Collisions happened more frequently. Smaller black holes that merged could accumulate mass faster than any individual black hole could through accretion alone. Gravitational wave detectors have now confirmed that black hole mergers occur in the present universe. Perhaps in the past they were far more common. What makes these early supermassive black holes cosmologically significant extends beyond the puzzle of their formation. They were not passive objects. As matter spiraled into them, they released enormous amounts of energy that heated surrounding gas, influenced star formation rates, and shaped the structure of their host galaxies. Supermassive black holes regulate galaxy growth. Finding them active so early means they were shaping cosmic evolution from nearly the very beginning. Their influence on the early universe was not a late addition to the story. It was a founding chapter. The energy emitted by an actively feeding supermassive black hole, called a quasar, can exceed the combined light output of every star in its host galaxy. A single quasar can shine with the luminosity of 1 trillion suns. Webb has detected quasars existing when the universe was less than 700 million years old. One particular object identified in Webb's observations shines with the equivalent luminosity of 600 trillion solar masses, more energy output than our entire galaxy produces, concentrated in a region perhaps a few light months across. The light from this object has been traveling for over 13 billion years, streaming in all directions through space the entire time, with only an infinitesimal fraction happening to reach Earth and Webb's detectors. Quasars serve a second function for astronomers beyond being extreme energy sources. Their intense light illuminates gas clouds that lie between them and Earth. When that light passes through a gas cloud, specific atoms absorb specific wavelengths, leaving characteristic gaps in the quasar's spectrum when observed from Earth. By analyzing these absorption patterns in quasar light, scientists map the composition, temperature, and distribution of intergalactic gas along lines of sight spanning billions of light years. This technique has helped reconstruct the three-dimensional structure of the cosmic web in ways that direct galaxy surveys cannot easily achieve. The cosmic web is the largest confirmed structure in the universe. Every galaxy, every cluster, every observable mass concentration in the cosmos exists on or near its threads. Dark matter filaments stretch for tens of millions to hundreds of millions of light-years, intersecting at massive nodes where galaxy clusters accumulate. Between the filaments lie voids, vast underdense regions extending for hundreds of millions of light-years in every direction, containing almost no galaxies and almost no ordinary matter. The web formed from the same tiny density fluctuations present in the universe moments after the Big Bang. Regions slightly denser than average exerted slightly more gravity, pulling in more matter, becoming denser still, and gradually amplifying over billions of years into the filaments and nodes we observe today. Regions slightly less dense than average lost matter to their surroundings, becoming progressively emptier as surrounding denser regions drained them. Over time, this process created increasingly stark contrast between full and empty regions. Think of a landscape after a heavy rain, where water flows downhill to collect in valleys. The valleys correspond to regions of high dark matter density. The slopes and ridges represent the filaments where matter flows from one concentration to another. Over cosmic time, this gravitational drainage has organized nearly all matter into the web's thin threads and dense intersections, leaving behind the vast voids that dominate the universe's volume. Dark matter provides the invisible scaffolding for this structure. It makes up 85% of all matter in the universe and does not interact with light. We detect it solely through its gravitational effects on visible matter and on light paths. For decades, scientists theorized that dark matter should line the cosmic web's filaments, threading through them from the most massive clusters down to the smallest connecting threads that link individual galaxies to larger structures. Mathematical models predicted this clearly, and simulations showed it explicitly, but nobody had directly observed dark matter on the filament's thinnest segments. A team of researchers using the Subaru telescope in Hawaii recently achieved this direct detection. They studied the Coma cluster, a dense collection of over 1,000 galaxies located 321 million light-years from Earth, and examined its surrounding network of cosmic web filaments. Using gravitational lensing, the slight warping of background galaxy shapes caused by intervening mass, they detected dark matter along the terminal segments of cosmic web filaments, the thin threads connecting the main structures to individual galaxies. This marks the first time dark matter was detected on the web's smallest connective threads, confirming that the invisible scaffolding genuinely pervades the entire network rather than concentrating only at the most massive nodes. The Coma cluster itself sits on the Great Wall, one of the first and most dramatic large-scale structures identified in astronomical surveys. A sheet of galaxies hundreds of millions of light-years across, it represents the kind of large-scale pattern that could only emerge from the cumulative gravity of dark matter, organized on cosmic scales. Webb added another remarkable discovery to this picture of early large-scale structure. Astronomers analyzing its data found what they call the cosmic vine, a chain of at least 20 closely packed galaxies stretching more than 13 million light-years end-to-end, existing when the universe was only a few billion years old. For comparison, the entire Milky Way measures about 100,000 light-years across. The cosmic vine is 130 times longer. All 20 galaxies show a redshift of roughly 3.44, meaning their light traveled between 11 and 12 billion years to reach us. They existed at a time when such a large-scale, connected structure was not supposed to have had time to assemble. The cosmic vine's estimated mass of approximately 260 billion solar masses makes it one of the most massive structures yet discovered. At this cosmic epoch, it appears to be in the process of becoming a galaxy cluster, with member galaxies continuing to fall inward under their combined gravity. Over several billion years from the epoch we observe, they will likely merge into a single unified cluster. What puzzles researchers about the cosmic vine specifically is the state of its two largest galaxies. Spectral analysis shows that both have almost completely stopped forming stars. In the early universe, nearly all galaxies were actively producing new stellar populations at high rates. Finding galaxies that have already exhausted or lost their star-forming gas at this cosmic epoch is unexpected. One possibility is that major mergers between galaxies triggered intense but brief starbursts that consumed the available gas. Another is that the dense protocluster environment around them stripped their gas through ram pressure, the force a galaxy experiences when moving through the hot plasma that fills space between cluster members. Like a hand pressed against a car window at highway speed, The resistance does not come from the hand pushing through anything solid. It comes from the relative motion between hand and air. Gas in galaxies experiences the same kind of stripping as they move through their cluster environment. On an even larger scale, Webb produced the deepest census of galaxy groups ever compiled. A team of astronomers cataloged 1,678 galaxy groups and protoclusters spanning from 12 billion years ago to approximately 1 billion years ago. This catalog maps how groups of galaxies evolve across most of cosmic history. In the early universe, the groups appear chaotic. Irregular shapes, vigorous star formation, loosely assembled configurations still in the process of organizing. At later times, the groups show greater symmetry, declining star formation rates, and more compact configurations as gravity has had longer to settle the structures. The evolutionary sequence is visible in the data as a clear trend, confirming theoretical predictions about how dark matter halos accumulate and merge over cosmic time. Inside one of those early galaxies, designated GS 3073, Webb found something that had never been observed before: direct evidence for the first generation of stars. The spectrum of this galaxy contained an unusual chemical signature. The ratio of nitrogen to oxygen in its gas was strikingly high, measuring 0.46, far beyond what ordinary stellar populations produce. Standard stellar physics cannot generate this ratio. The nitrogen abundance was simply too extreme for any normal combination of star types, stellar ages, or supernova yields to explain. But one set of theoretical models had predicted exactly this signature. Primordial monster stars, sometimes called population 3 stars, were the first stellar generation in the universe. They formed from clouds of pure hydrogen and helium, the only elements that existed before any stars had lived and died. Modern stars form from gas enriched with carbon, oxygen, and other elements that help it cool efficiently, allowing gravitational collapse to proceed. Without these cooling agents, primordial gas clouds collapsed into far more massive objects. Population 3 stars may have weighed anywhere from 100 to 10,000 times the mass of our Sun, making them the largest stars the universe has ever produced. These objects burned at temperatures far higher than modern stars. Their cores processed hydrogen into helium with extreme efficiency, then began fusing helium into carbon. At these masses, the carbon-nitrogen-oxygen cycle that governs stellar energy production in massive stars operated with unusual intensity, generating enormous quantities of nitrogen. The stars were short-lived by astronomical standards, burning through their fuel in perhaps a few million years. They did not end their lives in ordinary supernova explosions. Objects this massive tend to collapse directly into black holes, with little of their outer mass being ejected. But during their brief lives, they drove intense stellar winds that scattered nitrogen-rich material into surrounding space. That material mixed with later stellar generations and remained encoded in the galaxy's chemical composition. What Webb detected in GS 3073 is the residue of stars that lived and died billions of years ago, before any of the stars we see in the modern universe formed. The chemical fingerprint they left persisted across cosmic time, preserved in the gas and stars of later generations, and encoded in light that traveled to Webb's detectors. Over 12 billion years of cosmic expansion. This discovery matters for several reasons beyond confirming a long-standing theoretical prediction. Population 3 stars help solve the early supermassive black hole problem. If the first stars in the universe weighed thousands of solar masses and collapsed directly into black holes of equivalent mass, those black holes would begin their existence as massive objects rather than the 10 to 100 solar mass remnants of ordinary stellar collapse. Starting massive means reaching supermassive status much faster. A black hole seeded by a 10,000 solar mass population 3 star only needs to grow by a factor of 100,000 to become a billion solar mass supermassive object. That is a far easier problem than growing from 10 solar masses by a factor of 100 million. Population 3 stars may be the explanation for why supermassive black holes existed so early. These first stars also played a central role in a process called cosmic reionization. In the universe's early epochs, space was filled with neutral hydrogen gas, opaque to ultraviolet light. The first stars and galaxies emitted intense ultraviolet radiation that stripped electrons from surrounding hydrogen atoms, a process called ionization. As more sources of radiation formed and switched on across the universe, Regions of ionized gas grew and merged until the entire cosmos was reionized, making the universe transparent to light in the way we observe it today. Population 3 stars, with their extreme ultraviolet output, were likely among the primary drivers of this transformation. Webb's observations of the reionization epoch are actively testing models of how this process unfolded. The first stars also manufactured the first heavy elements. Every atom heavier than helium in the early universe came from stellar interiors: carbon, oxygen, nitrogen, silicon, iron. All of these had to be forged inside stars before they were available to seed planetary formation and chemistry. Population 3 stars did this first and did it fast. Their extreme mass and temperature allowed them to process gas into heavy elements at rates that ordinary stars cannot match. The enrichment of the early universe began with these giants. Understanding the full picture of early cosmic chemistry requires tracking how elemental abundances evolved across cosmic time, and this is something Webb is uniquely equipped to do. By analyzing spectra from galaxies at many different distances, corresponding to many different cosmic epochs, astronomers can trace how the concentrations of different elements changed as successive generations of stars lived, processed gas, and died. The earliest galaxies Webb has detected show spectral lines primarily from hydrogen and helium, with only faint traces of heavier elements. This is consistent with gas that has experienced minimal stellar processing. At intermediate distances, the heavy element content rises steadily. In the nearby universe, galaxies like the Milky Way show the full periodic table's worth of elements enriched by billions of years of stellar generations. This gradient is called chemical evolution, and it follows a predictable pattern with one significant wrinkle. Different elements enrich on different timescales. Oxygen is produced primarily in massive stars that live fast and die young as core collapse supernovae. Iron is produced more heavily by lower mass stars that live longer and die as type Ia supernovae. The ratio of oxygen to iron in a galaxy's spectrum therefore encodes information about the history of its star formation. A galaxy with high oxygen to iron ratios formed most of its stars rapidly in an intense early burst. A galaxy with lower oxygen to iron ratios has been forming stars steadily over a long time, allowing the slower iron-producing channels to catch up. Webb's chemical analyses across cosmic time are helping reconstruct not just how much enrichment happened, but how quickly and in what environments it occurred most intensely. Dense regions where galaxy mergers triggered starbursts enriched their gas rapidly. Isolated field galaxies enriched more slowly. The cosmic web's architecture influenced where enrichment proceeded fastest. Every atom heavier than helium in your body was forged inside a star and released through a supernova or stellar wind. The calcium in your bones, the iron in your blood, the oxygen in every breath, all of it was processed through stellar interiors and ejected into space before being incorporated into the molecular cloud that formed our solar system 4.5 billion years ago. This is not poetry. It is stellar nucleosynthesis, confirmed by spectroscopy, quantum mechanics, and nuclear physics. Webb's observations are filling in the detailed timeline of when and where this enrichment happened across the universe's history. Now consider the problem of light itself in all of this, specifically how the expansion of space transforms the nature of what we observe. When the galaxy JD's GS-Z14-0 emitted its light 290 million years after the Big Bang, that light left as a mix of ultraviolet and blue radiation characteristic of hot young stars. The photons began their journey as short wavelengths carrying high energies. Over the nearly 13.5 billion years since then, while those photons traveled toward us, the universe expanded by a factor of approximately 15 in linear scale. Every wavelength stretched by that same factor. Ultraviolet photons with wavelengths around 90 nanometers arrived at Webb's detectors, stretched to approximately 1,350 nanometers deep in the near-infrared. Visible light at wavelengths around 400 nanometers arrived, stretched to around 6,000 nanometers, well into the mid-infrared. The entire spectral energy distribution of this ancient galaxy shifted out of any wavelength range that human eyes or Hubble-style visible light telescopes could detect. This is why the Hubble Space Telescope, despite operating for over 30 years and producing some of the most scientifically productive images in astronomical history, could not see these objects. Hubble's instruments are optimized for ultraviolet and visible light, with some sensitivity extending into the near-infrared. Light from galaxies at extreme distances had been stretched far beyond Hubble's reach by the time it arrived. Those galaxies were not hidden by distance exactly. They were hidden by the physics of cosmic expansion, which had transformed their radiation into wavelengths no existing telescope could detect. Webb was designed from the beginning to solve this problem. Its instruments cover wavelengths from 0.6 microns to 28 microns, spanning the full near and mid-infrared range. This coverage captures redshifted light from galaxies at virtually any distance in the observable universe. The telescope operates at temperatures approaching absolute zero, essential because the detectors are sensitive, enough that the telescope's own thermal radiation would overwhelm the faint signals it is trying to measure, if any warmer than about -223 degrees Celsius. The difference between what Hubble and Webb see when pointed at the same region of sky is dramatic. Regions that appeared as black voids between Hubble's cataloged galaxies show up in Webb's images as filled with additional objects: faint red smudges, compact point sources, extended structures. The darkness was not empty. It was full of galaxies whose light had been stretched to wavelengths Hubble could not detect. Webb also sees through cosmic dust in a way Hubble cannot. Dense molecular clouds where new stars form are typically shrouded in thick blankets of dust particles that absorb and scatter visible light. These dust clouds appear as dark patches in Hubble images, blocking the view of whatever star formation is occurring inside. Infrared light passes through dust far more effectively than visible light. Webb reveals the hidden interiors of stellar nurseries that previous telescopes could only observe from the outside. The same effect operates across galaxies. Heavily dust-obscured galaxies that appear dim or entirely absent in visible surveys shine clearly in Webb's infrared observations. One of the most visually striking demonstrations of Webb's capability is its imaging of galaxy mergers in progress. When two galaxies fall toward each other under mutual gravity and begin to overlap, the interaction creates one of the most dramatic transformations in the universe. Gas clouds from the two systems collide at tremendous velocities, generating shock waves that compress the gas to extreme densities and trigger massive bursts of star formation. Thousands or millions of new stars ignite within a few million years, blazing in the merger region with intense blue and ultraviolet light that, at cosmological distances, arrives at Webb's detectors as infrared. Despite the violence of these events, individual stars within the merging galaxies rarely collide directly. Space inside galaxies is mostly empty. Stars are separated by light years. When two galaxies interpenetrate, their stellar populations pass through each other like two swarms of fireflies drifting through the same field. The stars mix without hitting each other. Only the gas is dense enough to produce shock interactions. The end state of a major merger between two comparable mass galaxies is an elliptical galaxy. The ordered rotation of spiral arms gets erased by the gravitational chaos of the merger. Stars end up on randomly oriented elliptical orbits around the merged center. Gas that has not been consumed in the starburst or expelled by feedback falls to the center, where it either fuels continued star formation or feeds the merged supermassive black hole produced when the two galaxies' central black holes spiral together under gravitational wave emission and coalesce. In approximately 4 billion years, the Milky Way and Andromeda galaxies will undergo this process. They are currently approaching each other at about 250,000 miles per hour. The merger will not be a single violent collision, but a slow-motion gravitational dance spanning several billion years, with the two galaxies making multiple close passes before finally merging. During and after this process, Earth's night sky will transform beyond recognition. Andromeda will grow from its current faint smudge into a sprawling structure filling a significant portion of the sky. New star clusters formed in the collision will blaze overhead. The final merged galaxy, sometimes nicknamed Milkdromeda, will be a massive elliptical containing the stellar populations of both progenitors. The Sun is unlikely to be significantly disturbed by the merger, since individual stellar collisions are so rare, but the night sky those future observers see will look nothing like ours. Webb also produced what may be the most striking demonstration of gravitational physics visible in a single image, a nearly perfect Einstein ring. This phenomenon requires an extraordinary alignment: a source galaxy, a massive foreground galaxy acting as a lens, and Earth must line up almost exactly along a single line of sight. When the geometry is close enough, the foreground galaxy's gravitational field bends the background galaxy's light into a ring surrounding the foreground object. Every photon from the background galaxy that passes on either side of the lensing mass gets deflected toward us, and the combination creates an arc that, in near-perfect alignments, closes into a complete ring. Einstein predicted this effect in 1915 as a consequence of general relativity, but he thought at the time that perfect rings would never actually be observed because the probability of exact three-body alignment across billions of light-years seemed impossibly small. He was wrong about the probability. Einstein rings have been found, and Webb has captured them with unprecedented clarity. These rings are more than visually striking. They are precision measurement tools. The radius of an Einstein ring depends on the mass of the lensing galaxy and the distances to both the lens and the source. By measuring the ring's angular size and combining it with distance information from redshift measurements, astronomers calculate the total mass of the foreground galaxy, including all its dark matter. This is one of the few methods available for directly measuring dark matter distributions in individual galaxies without any assumptions about how the dark matter is distributed. Results. From Einstein, ring analyses consistently show that dark matter halos extend far beyond the visible boundaries of galaxies. A galaxy may appear to have a well-defined disk 100,000 light-years across, but its dark matter halo can extend for several times that distance in every direction, forming an invisible spherical cloud of mass that dwarfs the luminous component. These measurements make it clear that the visible parts of galaxies we photograph are not the primary structures. They are the glowing centers of vast dark matter halos that are the actual gravitational anchors of galactic structure. Galaxy clusters produce even more dramatic lensing. When light from a distant background galaxy passes through a massive cluster, the combined gravity of hundreds of member galaxies plus hot intracluster plasma plus dark matter creates lensing effects far stronger than any individual galaxy can produce. Background sources get stretched into long arcs. Some appear multiple times as light travels different paths around the cluster. The resulting images can look like abstract art, crescents, partial rings, elongated smears, duplicated galaxy images. Astronomers exploit this deliberately. By pointing Webb at known massive clusters, they use those clusters as natural telescopes. The cluster's lensing magnifies background galaxies by factors of 10 to 100, bringing objects into view that would otherwise be far too faint to study in detail. Some of the most distant and faintest galaxies Webb has characterized were accessible only because a massive cluster happened to sit between them and us, amplifying their light. Without gravitational lensing, the cosmic archaeology Webb is conducting in the very early universe would not be possible with any realistically buildable telescope. These lensing measurements also provide independent confirmation of how much dark matter exists in clusters. Spectroscopic studies of cluster members show galaxies moving far too fast to be gravitationally bound by visible matter alone. Lensing measurements reveal the total mass distribution. Combining both methods consistently shows that dark matter comprises approximately 85% of the total mass in galaxy clusters. Ordinary matter in the form of stars and galaxies accounts for only a few percent. Hot plasma filling the space between galaxies makes up another 10 to 15%. The rest, the dominant constituent, is dark matter, detected only by its gravitational influence on light paths and galaxy motions. The voids between cosmic Webb filaments tell an equally important story. These regions are not simply featureless empty spaces. They are the largest continuous volumes of underdense material in the universe, stretching for hundreds of millions of light-years in some cases. The largest confirmed void spans approximately 1 billion light-years across. Light takes 1 billion years to cross it. From one edge to the other, traveling at the maximum possible speed, you would spend 1 billion years crossing essentially nothing before, reaching the nearest concentration of galaxies on the far side. Voids, formed through the same gravitational amplification that built the filaments, operating in reverse. Regions that started slightly less dense than average had slightly less gravitational pull. Matter drained out of them toward neighboring denser regions. As they lost matter, their gravity weakened further, causing them to lose matter even faster. This runaway process continued for billions of years. Voids grew larger as their interiors emptied into the surrounding filaments and walls. The cosmic web evolved by expanding voids and compressing filaments simultaneously, creating the increasingly stark contrast between full and empty regions we observe today. Scientists study voids carefully because they serve as exceptionally clean laboratories for measuring cosmic expansion and testing theories of dark energy. In dense regions like clusters and filaments, the motion of galaxies reflects a complicated combination of large-scale cosmic expansion and local gravitational pulls. Disentangling these effects is difficult. In voids, local gravitational effects are minimal. Galaxies within voids move primarily under the influence of the universe's overall expansion, making them nearly ideal test particles for measuring the expansion rate. Detailed surveys of void interiors provide independent measurements of the Hubble constant that help cross-check the two main methods and assess whether the tension between them is real or an artifact of some systematic error. The statistics of voids, their number, size distribution, and depth also test cosmological models directly. Standard cosmology makes specific predictions about how many voids of each size should exist given the initial density fluctuations and the properties of dark matter. Observing more or fewer voids, or finding them at the wrong characteristic sizes, would indicate problems with the standard model. Current observations match predictions well for voids, providing one of the stronger confirmations that the broad outlines of structure formation theory are correct, even as specific details regarding the early universe remain contested. Within the voids, any civilization that happened to form would inhabit a dramatically different observational environment than we do. Looking up from a planet inside a void, they would see far fewer galaxies across the sky. Their night sky would be darker, their view of the cosmos more limited. They might survey their observable universe and conclude it contains far less than it actually does, simply because their location placed them in one of the universe's sparse regions. Our location within a filament connected to the Virgo cluster and the larger Laniakea supercluster gives us a richer view than void-dwelling observers would have. Though it also means we are not in the typical location, the average point in the universe by volume sits inside a void, because voids make up most of the universe's total volume while concentrating almost none of its matter. Time itself behaves differently across cosmic distances, and this adds another layer of complexity to everything Webb observes. Einstein's theory of general relativity predicts two effects that alter the experienced rate of time depending on an observer's circumstances. Gravitational time dilation. Clocks in stronger gravitational fields run slower relative to clocks in weaker fields. Velocity time dilation. Clocks moving faster relative to an observer run slower from that observer's perspective. Both effects are real, precisely measured, and built into the design of GPS satellites, which would accumulate significant errors if not corrected for these relativistic effects. At cosmic distances, velocity time dilation becomes cosmologically significant. Galaxies at the edge of the observable universe are receding from us at speeds approaching the speed of light. Relative to us, their clocks tick slowly. From our perspective, time in those distant galaxies is dilated, proceeding at a fraction of the rate it does here. This is one reason why analyzing time-variable phenomena, like the way a supernova's brightness changes over days and weeks, requires correction when the supernova occurred in a distant galaxy. The observed time variation is stretched by the same factor that stretches the light's wavelengths. A supernova in a galaxy at redshift 1 will appear to vary twice as slowly as an identical supernova nearby because all time intervals from that distance are stretched by a factor of 2. This prediction of relativity has been verified by exactly these observations, confirming that time dilation is operating across cosmological distances, exactly as theory predicts. What this means, observationally, is that we view distant galaxies not just from afar, but from a different temporal frame of reference. The universe we observe is not a single moment in time, but a layered composite of many different epochs, each galaxy appearing as it existed at the cosmic moment corresponding to its distance and the travel time of its light. Looking up at the night sky is simultaneously looking into the past and looking across distances. Webb's deepest observations combine both effects to an extreme degree, revealing objects as they appeared when the universe was a tiny fraction of its current age, transformed by both their distance and the relativistic stretching of time in a rapidly expanding cosmos. As galaxies recede beyond the cosmic horizon, they do not simply vanish. From our perspective, they experience increasing time dilation as their recession velocity approaches the speed of light. Their light is stretched to longer and longer wavelengths, becoming first infrared, then microwave, then increasingly faint radio waves. Simultaneously, the rate at which their photons arrive at our detectors decreases because the expanding space between us and them increases the time between successive wave crests. Both effects reduce the detectable signal until the galaxy effectively disappears from observation, not because it is gone, but because it has crossed the threshold where no instrument can detect it. What remains behind that horizon is not nothing. The universe does not end at the edge of the observable sphere. Structure continues. Galaxies exist. The physical laws that govern matter, energy, and space in our region almost certainly continue without interruption in the regions beyond our horizon. The cosmological principle, the working assumption that the universe is roughly the same everywhere when viewed at large enough scales, is confirmed within our observable sphere and extended by inference beyond it. But it cannot be verified beyond the horizon. This is one of the hard boundaries of what science can know, not a limitation of technology or cleverness, but a fundamental constraint imposed by the finite speed of light and the accelerating expansion of space. Some cosmological models suggest our observable universe is one bubble in a much larger multiverse, regions of space that each underwent their own inflationary expansion and each contain their own physical parameters, including potentially different values of fundamental constants. The Standard Model's constants, the masses of particles, the strengths of forces, the value of dark energy might take different values in different inflationary bubbles. We cannot observe other bubbles. We cannot test this hypothesis directly. It sits at the boundary between physics and metaphysics, a mathematically consistent extrapolation from inflationary theory that may or may not correspond to something real beyond our horizon. What we can know is vast enough. The observable universe contains between hundreds of billions and trillions of galaxies, each containing hundreds of billions of stars, each potentially hosting planetary systems. The total number of planets in the observable universe alone is measured in hundreds of quintillions at minimum, possibly far more. The conditions that produced life on Earth, an average star in an average galaxy in an average region of space, are not special. They are common. Whether life has emerged elsewhere is unknown, but the raw material and the conditions are demonstrably widespread. One of the most puzzling features of Webb's early universe observations is summarized in a phrase astronomers have started using with increasing frequency: too much light, too early. The Standard Cosmological Model makes detailed predictions about how luminous the universe should be at each cosmic epoch. These predictions come from calculations of how quickly gas can collapse into stars given the density of matter, the temperature of gas clouds, the properties of dark matter, and the physics of gravitational collapse. The model is not a rough approximation. It incorporates decades of observational data, computational simulations, and theoretical refinement. It accurately predicts a wide range of observable properties, including the pattern of temperature fluctuations in the cosmic microwave background, the large-scale distribution of galaxies, the abundance of light elements produced in the first minutes after the Big Bang, and the overall expansion history of the universe. Yet when Webb measured the total luminosity of galaxies in the first billion years of cosmic history and compared those measurements to the model's predictions, the discrepancy was striking. The early universe was producing 2 to 10 times more light than the model allowed, depending on the specific cosmic epoch examined. Somewhere between twice and 10 times more, across multiple independent surveys in different directions on the sky, using different instruments and analysis methods, the same excess appears consistently. One category of explanation involves the initial mass function. This term describes the distribution of stellar masses when a population of stars forms. Modern star formation produces mostly low-mass stars, because the physical processes that fragment collapsing gas clouds tend to create fragments at the low end of the possible mass range. Massive stars are produced, but they are far fewer in number than low-mass stars. The problem is that massive stars are enormously brighter than low-mass ones. A star 10 times more massive than the Sun is not 10 times brighter. It is 10,000 times brighter. If the early universe somehow produced a higher fraction of massive stars when a cloud of gas collapsed, The resulting population would be far more luminous than an equivalent mass of stars formed under modern conditions. The same total mass of gas would produce dramatically more light. Whether the initial mass function actually differed in the early universe is unknown. There are theoretical arguments for why it might have. The first gas clouds were composed of pure hydrogen and helium, lacking the heavier elements that help gas cool efficiently in the modern universe. Cooling efficiency affects how large gas fragments become before gravitational collapse proceeds. In a less efficiently cooling gas, the minimum fragment mass that can collapse tends to be larger, which could produce more massive stars. But this is theoretical extrapolation, rather than confirmed observation. Direct measurement of the initial mass function in very early galaxies is currently beyond our technical capability. A second category of explanation involves star formation efficiency. In the modern universe, star formation is remarkably wasteful by cosmic standards. When a molecular cloud collapses, only a few % of its total mass actually ends up in stars. The rest is dispersed back into the interstellar medium by the radiation pressure and stellar winds from newly formed stars, by supernova explosions from the most massive stars, and by turbulent processes that prevent gravitational collapse from efficiently converting all available gas. If early galaxies had higher star formation efficiency, converting more of their gas mass into stellar mass before feedback disrupted the remaining material, they would again produce more light per unit of available gas. Direct collapse black holes, if they existed, could have contributed to the excess light problem indirectly. By creating supermassive black holes very early, they would have produced early active galactic nuclei, which in some models enhance star formation in surrounding gas by providing pressure waves that trigger cloud collapse. Whether this effect is large enough to significantly influence galaxy scale luminosities is uncertain. Webb's discovery of abundant active galactic nuclei in early galaxies may also partially explain the excess light. Active galactic nuclei powered by accreting black holes can be brighter than entire galaxies of stars. If many early galaxies harbored unusually bright central engines, those objects would contribute significantly to the total luminosity budget of the early universe, in ways that standard models, which focus primarily on stellar light, may underestimate. What makes the too much light problem especially challenging for theorists is its consistency across cosmic epochs. If it were a one-time anomaly at a specific early time, it might be explained by some transient condition. But Webb keeps pushing the observed excess to earlier and earlier epochs. Galaxies at 500 million years were brighter than predicted, then at 400 million years, then at 300 million years, then at 290 million years. Each new distance record extends the challenge backward in time, suggesting whatever mechanism produced the excess was operating from very early in cosmic history. The problem is not that the standard model is completely wrong. It accurately describes most of what we observe across most of cosmic history. The problem is that it is missing something important about the first few 100 million years. Whether that missing ingredient is astrophysical, involving unknown properties of star formation or black hole growth, or cosmological, involving unknown physics in the dark matter or dark energy sector, is currently unknown. Resolving this question is one of the primary scientific goals driving continued Webb observations. Alongside all these questions about the early universe, Webb is contributing equally important insights about the present and near-past cosmos, including the detailed structure of individual galaxies and how their properties relate to their environments. The process of environmental quenching is one of the clearest demonstrations that a galaxy's history is not determined solely by its internal properties. Two galaxies with identical initial conditions can evolve into dramatically different objects, depending entirely on where they end up in the cosmic web. Consider a spiral galaxy, forming in isolation in a field environment, far from any major cluster. It draws in a continuous supply of fresh gas from surrounding cosmic web filaments. The gas cools and condenses into molecular clouds that fragment into new stars at a steady rate. As those stars age, the most massive ones die in supernova explosions that inject energy into the interstellar medium, heating some gas and expelling it in galactic winds, but not disrupting the overall star-forming cycle. The galaxy maintains an equilibrium between gas accretion, star formation, and feedback. Over billions of years, it builds a large stellar population and may remain actively star-forming for most of the universe's current age. Now consider the same galaxy falling into a massive cluster. As it approaches the cluster and crosses into the hot intracluster medium, it begins to experience ram pressure. Gas from the galaxy's outer regions, where the gravitational potential is relatively shallow, gets pushed backward relative to the galaxy's direction of motion. Long tails of gas and star-forming material trail behind the galaxy as it plunges deeper into the cluster. These tails can extend for hundreds of thousands of light-years. The gas in them continues forming stars for a brief period, creating a spectacular trailing chain of stellar birth that Webb has captured in multiple systems. Eventually, the stripped gas disperses into the hot intracluster medium and is lost. The galaxy's reservoir of star-forming material declines. Star formation slows and eventually stops. The existing stellar population ages in place, its most massive stars dying first, leaving behind progressively older, redder stars. The galaxy changes color from blue, indicating active star formation, to red, indicating an old stellar population without ongoing formation. The transformation from actively star-forming to quiescent can happen in as little as a few 100 million years, once a galaxy has fallen deep into a cluster. Webb sees this process at multiple stages. Some galaxies show trails of stripped gas still actively forming stars. Others show evidence of recent quenching, stellar populations that stopped forming relatively recently based on their color and spectral characteristics. Still others are deeply quiescent, their gas long gone, their stellar populations aging uniformly. The range of stages visible in a single cluster image tells the entire story of environmental transformation across cosmic time. What this process accomplishes on a large scale is the separation of the galaxy population into two broad categories, active and passive. Active galaxies are forming stars, consuming gas and typically blue in color. Passive galaxies have stopped forming stars, are slowly dying in a stellar population sense, and appear red. The fraction of passive versus active galaxies in the universe has increased over cosmic time as more and more galaxies have fallen into cluster environments and been quenched, or have exhausted their internal gas supplies through prolonged star formation and been shut down by their own feedback processes. Webb's ability to track this transition across different distances, corresponding to different cosmic epochs, allows astronomers to measure when the balance tipped. The universe was once dominated by actively star-forming galaxies. At some point in cosmic history, the passive population grew to match and then exceed the active one. When exactly this transition happened, and whether it proceeded uniformly across all environments or happened earlier in dense regions and later in the field, are questions Webb's observations are actively constraining. The answers matter because they connect to broader questions about why the universe is the way it is today. The stellar mass assembled in galaxies across cosmic time, the chemical enrichment of the interstellar and intergalactic medium, the number and properties of planets that formed around successive stellar generations, all depend on the history of star formation across the universe and the processes that created and ended it. Star formation itself seems to have operated differently in the early universe, and not only because galaxies were gassier and more chaotic. The rate at which early galaxies converted available gas into stars, measured in solar masses of new stars produced per year, was dramatically higher than equivalent galaxies produced today. A galaxy at a redshift of 2, existing when the universe was about 3 billion years old, might be forming stars at a rate of several hundred solar masses per year. A comparable galaxy today might form only a few solar masses per year, sometimes less. The early universe was a period of intense stellar productivity, with individual galaxies operating at efficiencies that modern galaxies rarely achieve. Some of this elevated star formation rate reflects the greater abundance of gas in early galaxies. Galaxies had not yet consumed much of their initial gas supplies, so more was available as raw material, but the elevated rates are not entirely explained by gas abundance alone. Early galaxies converted their gas into stars more efficiently per unit of available material than modern galaxies do, suggesting that the physical conditions of star formation were different in the denser, hotter, more turbulent early universe. Galaxy mergers contributed significantly to elevated early star formation rates. When two gas-rich galaxies collide, the interaction channels gas toward the galactic center in concentrated streams, triggering starbursts that can produce thousands of solar masses of new stars per year for brief periods. The early universe, with its smaller average galaxy separations and higher encounter rate, experienced far more frequent mergers than the present universe does. Cosmic expansion has since diluted the galaxy population enough that major mergers are considerably rarer today. Understanding the interplay between merger rates, gas content, star formation efficiency, and feedback processes across cosmic time is one of the central challenges of contemporary extragalactic astronomy. Webb's observations are not solving this problem cleanly, but they are providing the most detailed, empirical map of these processes across cosmic history that has ever been assembled. There is a deeper strangeness to all of this that physicists rarely dwell on in public but think about constantly in private. The observable universe is not just big. It is big in a very specific, finely tuned way that appears necessary for anything in it to exist at all. Consider the cosmic expansion rate. If the universe had expanded just slightly faster in its first moments, matter would have dispersed too quickly for gravity to pull it into the first stars and galaxies. The initial density fluctuations that seeded all structure would have been smoothed away before they could amplify. The universe would have expanded forever as a nearly uniform fog, never forming anything interesting. If expansion had been slightly slower, gravity would have won the competition against outward motion. The universe would have recollapsed in a big crunch long before life could emerge anywhere. The expansion rate was calibrated in the first fraction of a second with extraordinary precision, too precise by some calculations to be a coincidence of initial conditions without explanation. The strength of dark energy presents a similar puzzle. The value physicists measure for dark energy, derived from supernovae observations and cosmic microwave background analysis, is about 120 orders of magnitude smaller than the naive prediction from quantum field theory. 120 orders of magnitude is not a small discrepancy. It is the largest known gap between a theoretical prediction and an experimental measurement in all of science. Quantum field theory predicts that empty space should be teeming with vacuum energy at an enormously high density. Yet the observed dark energy density is essentially zero by comparison. Something is suppressing the quantum vacuum energy to nearly nothing, leaving only this tiny residual value. Nobody knows what that something is. This is called the cosmological constant problem, and it has been unresolved for decades despite being one of the most actively studied problems in theoretical physics. Had dark energy been even slightly larger than it is, the accelerated expansion it drives would have prevented the formation of galaxies entirely. The first density fluctuations after the Big Bang would have been blown apart by the rapidly expanding space before gravity could amplify them into the first stars. A universe with larger dark energy would be permanently empty. Had it been negative, the universe might have recollapsed into a crunch before life could evolve. The specific value of dark energy we observe is one of the most puzzling facts about our universe. Theoretical physicists do not have a satisfying explanation for why it is what it is, rather than something larger, smaller, or zero. Similar precision appears in the strength of the strong nuclear force that holds atomic nuclei together. If this force were a few percent stronger, all hydrogen in the early universe would have been converted into helium in the first minutes, leaving no hydrogen available to form water or fuel hydrogen-burning stars like our Sun. A few percent weaker and nuclear reactions in stellar cores would not proceed efficiently enough to power stars. The specific value we observe is in a narrow range that permits the chemistry of life. Physicists call this collection of observations the fine-tuning problem. The fundamental constants of nature appear calibrated to values in the narrow ranges that permit a universe complex enough for stars, planets, chemistry, and eventually observers to exist. Whether this reflects some unknown physical principle that constrains the constants, whether it reflects selection effects in a larger multiverse, where most regions have different and uninhabitable constants, or whether it reflects something else entirely, remains one of the deepest open questions at the interface of physics and cosmology. Webb's observations do not directly address fine-tuning, but they contribute to the picture by demonstrating just how precisely the universe's initial conditions were set. The distribution of galaxies, the sizes of voids, the clustering of matter on large scales, all of these are sensitive to the initial density fluctuations that were generated in the first moments after the Big Bang. Webb's deep surveys are providing the most detailed maps of these structures across cosmic history, allowing physicists to constrain the properties of the initial conditions more precisely than ever before. Cosmic inflation, The theoretical period of exponential expansion, believed to have occurred in the first tiny fraction of a second, is the leading explanation for why the initial conditions were set the way they were. Inflation stretches quantum fluctuations in the density of the early universe to macroscopic scales, producing the pattern of density variations that seeded all subsequent structure formation. Different versions of inflation make subtly different predictions about the statistical properties of these fluctuations. Webb's observations of the large-scale galaxy distribution, combined with cosmic microwave background measurements from satellites like Planck, are gradually distinguishing between different inflationary models and constraining the physics of that earliest cosmic moment. What Webb cannot do, and what no instrument can ever do, is observe beyond the cosmic horizon. The physics of light and expansion create a hard boundary around every observer in the universe. Whatever lies beyond our horizon is, in a genuine and not merely practical sense, unknowable from our location. Not just hard to measure, causally inaccessible. No signal generated anywhere beyond the horizon can reach us. We are isolated within our observable sphere in the same way that two planets on opposite sides of a black hole's event horizon are isolated from each other. The universe we can see contains extraordinary variety and complexity. The universe we cannot see may contain more of the same, or it may differ in ways we cannot anticipate. The honest answer is that we do not know, cannot know, and may never be able to know. Science operates within the boundary of what is empirically accessible. The realm beyond the cosmic horizon sits outside that boundary, possibly forever. Yet what we can see is already more than enough to demand rethinking our assumptions at almost every level. The universe is 13.8 billion years old. The observable portion spans 93 billion light-years. It contains somewhere between 200 billion and 2 trillion galaxies, each hosting hundreds of billions of stars, each potentially surrounded by planets. The first structures formed remarkably early, within 300 million years of the Big Bang, in defiance of what the Standard Model predicted. Supermassive black holes existed when the universe was less than 500 million years old. The first generation of stars weighed thousands of solar masses and blazed briefly before collapsing into the seeds of those early black holes. Dark matter provides the invisible scaffolding on which all visible structure hangs. Dark energy dominates the universe's energy budget and is driving accelerated expansion that will eventually sever our causal connections to most of the cosmos. The expansion rate of the universe, when measured by different methods, gives different answers that current theory cannot reconcile. Any one of these facts would be scientifically significant. Together they constitute a coherent demand for new physics. The standard cosmological model is not merely slightly imperfect. It is facing systematic challenges at multiple fronts simultaneously, challenges that Webb is documenting with unprecedented precision. This is exactly what scientific progress looks like from the inside, not a gradual smooth accumulation of confirming evidence, a collection of precise anomalies that mark the boundary of current understanding and point, without clearly indicating the direction toward something beyond it. The telescope has now been operational for over 2 years. Its planned mission duration is at least 10 years, with fuel reserves that might extend its operation to 20 years or beyond. The discoveries of its first 2 years are already transforming multiple fields simultaneously. The next 2 decades of observations will provide the detailed follow-up needed to distinguish between the competing explanations for what, in those early discoveries, revealed. Researchers are working to better constrain the properties of the earliest galaxies by obtaining spectroscopic data for larger samples rather than relying on photometric redshift estimates, which are less precise. Spectroscopy requires much longer observing times per target, but it provides reliable distance measurements and chemical composition information that photometry alone cannot. A systematic spectroscopic survey of the most distant galaxy candidates in Webb's imaging will take years, but it will distinguish between objects that truly exist at extreme distances and contaminating sources that merely appear distant due to photometric confusion. Dark matter models are being tested against Webb's large-scale structure observations. The standard cold dark matter model predicts a specific abundance of galaxy clusters and filaments at each cosmic epoch. If dark matter has different properties than assumed, perhaps being warm rather than cold, meaning its particles moved more rapidly in the early universe and erased small-scale density fluctuations, the distribution of observed structures would differ in measurable ways. Webb's deep census of early galaxy groups and clusters provides one of the strongest constraints yet on alternative dark matter models. The Hubble tension is being attacked from multiple directions simultaneously. Ground-based experiments are improving measurements of Cepheid variable star distances. The Event Horizon Telescope collaboration is working on a complementary distance measurement technique using megamasers, naturally occurring microwave amplifiers in galaxy nuclei. If a new measurement method returns the same local expansion rate as existing Cepheid and supernova measurements, the tension with the early universe prediction becomes even harder to dismiss as a systematic error. If a new method returns a different value, it would point toward where the existing measurements may be going wrong. Gravitational wave astronomy is providing an entirely new channel for measuring the Hubble constant. When two neutron stars or black holes merge, they produce gravitational waves that encode information about the absolute distance to the merger. If those mergers also produce electromagnetic signals that allow host galaxy identification, astronomers can measure both the distance and the recession velocity independently, giving a completely self-contained expansion rate measurement. As the gravitational wave detector network becomes more sensitive and accumulates more merger events, this method will provide increasingly precise Hubble constant values that are entirely independent of the Cepheid supernova distance ladder. Cosmic reionization is under intense investigation. The epoch when the first stars and galaxies transform the universe from opaque to transparent is directly accessible to Webb in the observations it is already making. The topology of reionization, how patchy it was, how rapidly it progressed, which sources drove it, are all encoded in the spectra of distant galaxies and quasars. Resolving these questions will clarify the role of population 3 stars in the early universe and constrain models of how the first galaxies formed and influence their surroundings. The too much light problem, the systematic excess of early galaxy luminosity compared to standard model predictions, will be addressed by more complete surveys of the early galaxy population. Current surveys, though unprecedented in depth, cover only small fractions of the sky. Wider surveys at somewhat lower depth will establish whether the excess is truly uniform across the sky or whether it reflects the particular regions already observed. Theoretical work continues to explore whether changes to star formation physics, dark matter properties, or the initial conditions of cosmic structure can account for the discrepancy without requiring entirely new physics. All of these efforts share a common foundation. The James Webb Space Telescope is producing data of a quality and depth that previous astronomy could not approach. The instrument is working exactly as designed. Its mirror, its detectors, its infrared sensitivity, its deep space position, all are performing as engineers intended. The mission is not constrained by instrumental limitations. It is constrained only by the size of the science case, which turns out to be essentially unlimited. We built a machine capable of seeing light that has been traveling for 13.5 billion years. We pointed it at patches of darkness and found entire populations of galaxies that nobody knew existed. We found those galaxies misbehaving, growing too fast, shining too brightly, harboring chemical elements that should not yet have been forged, surrounding supermassive black holes that should not yet have grown. We found the universe was 7 times wider than intuition suggested, and that its expansion rate cannot be pinned to a single agreed-upon value. We found the first direct evidence for types of stars that existed only in theory, burning in the universe's first 300 million years before any telescope on Earth existed to see them. What comes next from Webb will not resolve all of these mysteries. Science rarely works that cleanly. It will refine them, constrain them, distinguish between possible explanations, and almost certainly reveal new anomalies that pose new questions. The universe has not run out of surprises. Webb has barely started looking. If you found this exploration of the cosmos engaging, sharing it with someone who has not considered the true scale of what exists is one of the simplest ways to spread this kind of perspective. The universe is vast enough that no one person and no one generation can fully absorb what it contains. Every new set of eyes brings new questions, and new questions are where science begins. The scale of what Webb has revealed is genuinely difficult to hold in mind. 93 billion light-years across, trillions of galaxies, a timeline of structure formation that precedes all biological life on Earth by billions of years, and extends into a future when the last of those structures will cool and fade into darkness. We exist in an extraordinary moment, early enough in cosmic history that the universe is still young and active, equipped with instruments sensitive enough to read its oldest light, and capable of asking questions that no prior era of human existence could have even formulated clearly. The darkness is not empty. We know that now, more thoroughly than ever before. And with every hour of observation, Webb accumulates. The picture of what the darkness contains becomes richer, stranger, and more precise. To appreciate the full context of what Webb is doing, it helps to trace the history of how humanity's view of cosmic scale has changed, because the pattern of revision is itself remarkable. Each major breakthrough in observational astronomy has not merely extended the known universe by a modest amount, it has revealed that the previously known universe was a vanishingly small fraction of what actually exists. In the early 17th century, Galileo turned one of the first telescopes toward the sky and resolved the Milky Way into individual stars. The band of light across the night sky, previously treated as a kind of luminous vapor, turned out to be millions of distinct stellar points too close together for the naked eye to separate. The scale of the known universe doubled, then doubled again, then kept expanding as the telescope revealed that stars are distant objects of the same basic type as our own sun. By the early 20th century, astronomers understood that the Sun was one of roughly 100 billion stars in the Milky Way, arranged in a disk roughly 100,000 light-years across. This seemed to constitute the universe. The faint spiral nebulae visible in long-exposure photographs were thought to be structures within or near the Milky Way, nearby clouds of gas and dust in the process of forming planetary systems. In 1924, Edwin Hubble used the 100-inch telescope at Mount Wilson Observatory to resolve individual Cepheid variable stars in the Andromeda Nebula and measure their distances. The results showed that Andromeda was not inside the Milky Way. It was not even close. It was a separate galaxy, roughly 1 million light-years away, later revised to 2.5 million, comparable in size to our own. The spiral nebulae were not nearby gas clouds. They were island universes comparable to the Milky Way, separated from it by abyssal distances. The universe expanded in a single observational stroke from one galaxy to millions, then hundreds of millions, then billions, as surveys revealed more and more distant galaxies in every direction. In 1929, Hubble showed that distant galaxies were receding from us at speeds proportional to their distances, the relationship that now bears his name. This observation demonstrated that the universe was expanding. Running the expansion backward in time led to the conclusion that all matter was once compressed into an enormously hot, dense state. The Big Bang Theory followed, and with it a new understanding of cosmic time. The universe had a beginning approximately 13.8 billion years ago. Each revision in our understanding of scale forced a corresponding revision in our understanding of time. A larger universe meant more room for complexity to emerge. More time meant more opportunity for stellar generations to enrich the cosmos with heavy elements, for planetary systems to form, for chemistry to assemble into biology, for biology to eventually produce minds capable of asking these questions. Now Webb is forcing another revision. The universe is not just large, it is populated more densely than previous surveys revealed, with more galaxies, more early structure, more chemical complexity at earlier times than standard models predicted. Every extension of observational reach into the past has revealed a cosmos that was more active, more structured, and more complex at earlier times than the model previously standing expected. This pattern of expectations consistently underestimating cosmic productivity may itself be telling us something. Perhaps the universe generates structure and complexity more readily than current physics suggests. Perhaps the processes that produce galaxies, stars, and eventually planets are more robust, more efficient, and more universal than our models capture. The consistent direction of surprise, toward more structure earlier, suggests a systematic gap in understanding rather than a collection of random anomalies. The history of astronomy is a history of displacement followed by expansion. Each generation believes it has grasped the rough outline of cosmic reality, only to have the next generation's instruments reveal a richer picture that makes the previous one look provincial. There's every reason to expect this pattern will continue. Webb is the most powerful observatory humanity has ever constructed, and within the first 2 years of its Operation, it has already revealed that the universe is stranger and richer than the model that preceded it described. What Webb has not done is make the universe comprehensible in the sense of fitting comfortably within human experience. The numbers remain as staggering as ever. 93 billion light-years is not a distance that any human can genuinely visualize. 13.8 billion years is not a time span that biological intuition can span. Trillions of galaxies, quintillions of stars, astronomical numbers of planets. These figures are processed intellectually without being felt. They are communicated in words that carry emotional weight, but the actual quantities involved are too large for direct intuition. This is not a failure of science or communication. It is an honest consequence of the fact that the universe is genuinely vastly larger than the scale at which evolution tuned human cognition. We evolved to navigate a world of objects from millimeters to kilometers in size, separated by distances from meters to perhaps hundreds of kilometers. Nothing in the survival pressures of primate evolution required an intuitive grasp of megaparsecs or gigayears. The cognitive tools we use to understand cosmic scales are borrowed from domains they were not designed for, which is why the numbers can be stated without being felt. Webb cannot fix this. What it can do is provide precise data that constrains the equations describing cosmic reality at scales from individual stellar systems to the observable universe as a whole. Those equations, when applied correctly, make predictions that can be tested. When the tests pass, the equations are trusted. When they fail, as they are currently failing in specific ways regarding early galaxy formation and the expansion rate, the equations are revised. This process of measurement, prediction, and revision is how science extends reliable understanding beyond the boundaries of intuition. The revisions currently in progress may lead to genuinely new physics. The Hubble tension could resolve into evidence for new particles, new fields, or new behavior of dark energy. The too much light problem could require modifications to how stars form in low metallicity environments or how dark matter halos behave at high redshift. The early supermassive black holes could lead to direct observational evidence for direct collapse black holes or population 3 stellar remnants. Each of these would represent not merely a refinement of existing theory, but the addition of genuinely new physics to the scientific picture, or the resolution might be more mundane. Systematic errors sometimes survive longer than expected in scientific measurements. Alternative explanations sometimes turn out to be correct after initially appearing less compelling. The history of science contains examples of both dramatic paradigm shifts and more conservative resolutions of apparent anomalies. Webb's data will tell us which category the current set of tensions falls into. What is certain is that the data Webb is collecting represents a permanent addition to human knowledge. The observations of galaxies at redshift 14, the spectra of early galaxies revealing unexpected chemistry, the census of 800,000 galaxies in a single field, the Einstein rings, the cosmic vine, the quiescent galaxies at extreme distances. All of this is now known in a way it was not before the telescope launched. It cannot be unknown. Whatever theoretical picture eventually accommodates these observations will have to account for them, and in doing so, it will be more accurate than the one that preceded it. In a universe that will eventually cool into darkness over timescales incomprehensibly longer than its current age, the particular moment we inhabit is one of unusual richness. Galaxies are still forming stars. The cosmic web is still actively channeling matter into clusters. Active galactic nuclei are still blazing. The universe is middle-aged by some measures, past its peak of star formation, but nowhere near its end. We happen to arrive at a time when structure is fully developed enough to produce complex chemistry and biology, but young enough that most of the universe's structural features remain visible and accessible. We are also living in the narrowing window of observational access. In a few tens of billions of years, the accelerating expansion will have swept most galaxies beyond our horizon. Future observers will inhabit a universe that appears almost empty compared to ours, with only the local group visible in a sky that is otherwise dark. They will have no direct evidence that billions of other galaxies once filled that sky. They will be looking at the same universe we occupy now, but they will see almost none of it. We can see it. Right now, with Webb pointed at a patch of sky slightly larger than 3 full moons, the light of 797,000 galaxies is falling on its detectors. Each of those galaxies is a universe of stars in its own right. Each represents billions of years of cosmic history encoded in photons that have been traveling through expanding space since before the Earth existed. The universe is larger, older, more structured, more chemically rich, and more dynamically active than any previous generation of astronomers knew. Webb is the instrument that has most recently and most dramatically extended that knowledge. What it finds in the years ahead will continue to reshape the picture, as every major observatory in history has reshaped the picture it inherited. The darkness between the stars is full of light we cannot see. Webb has made some of it visible. The rest is still out there, waiting. The specific instrument responsible for many of Webb's most detailed early universe characterizations is the near-infrared spectrograph, called NIR-SPEC. This device can observe up to 200 galaxies simultaneously by positioning tiny shutters, each the width of a human hair, to collect light from pre-selected targets across a field of view. Each set of shutters creates a spectrum, a complete record of how much light the target emits at every wavelength across the near-infrared range. From these spectra, astronomers extract redshifts, chemical compositions, star formation rates, gas temperatures, and black hole activity for every target in a single observation. The ability to spectroscopically characterize hundreds of targets simultaneously, rather than one at a time as was required with previous spectrographs, is a qualitative change in how deep field surveys operate. Programs that would have required thousands of nights of telescope time with Hubble spectrographs can be completed in dozens of nights with Webb's NIR-SPEC. This efficiency is why Webb accumulated the spectroscopic confirmation of JAD's GS cell 220 within months of identifying it photometrically, whereas confirming record-breaking Hubble candidates sometimes took years. The mid-infrared instrument, called MIRI, extends Webb's wavelength coverage to 28 microns, accessing radiation from the most distant galaxies that has been stretched by the greatest factors. It also observes mid-infrared emission from nearby objects with a clarity that reveals processes invisible at shorter wavelengths, including the emission from warm dust in star-forming regions, the signatures of molecular gases in planetary atmospheres, and the thermal emission from cool objects like brown dwarf stars and directly imaged exoplanets. The near-infrared camera NERCam is the primary imaging instrument. It produces the sweeping wide-field views that have become icons of the mission, including the deep-field images that revealed the hundreds of thousands of galaxies in the Cosmos Webb field. NERCam simultaneously images two separate patches of sky in multiple infrared wavelengths, allowing color information to be collected during a single exposure rather than requiring separate observations at each wavelength. This multiplexing efficiency is why Webb can assemble the spectral energy distributions needed for photometric redshift estimates for hundreds of thousands of objects in a single deep field observation. Behind these technical capabilities lies an engineering achievement that took decades. The telescope's primary mirror is too large to fit inside any existing rocket fairing in its fully deployed configuration. It had to be folded for launch and then unfolded in space through a precisely choreographed sequence of deployments spanning 2 weeks. 18 hexagonal gold-plated beryllium mirror segments had to unfold and then be aligned to within a fraction of the wavelength of infrared light, a tolerance of about 50 nanometers, corresponding to about 1,000th the diameter of a human hair. If any mirror segment was misaligned by more than this, the telescope's resolution would be compromised. The alignment succeeded completely. The sun shield, a 5-layered diamond-shaped structure roughly the size of a tennis court, had to deploy without a single tear or tangle to protect the telescope's cold instruments from the warmth of the sun, earth, and moon. The instruments operate at temperatures near -223 degrees Celsius. Even the warmth of starlight from the wrong direction would overwhelm the faint infrared signals the telescope is trying to detect. The sunshield deployment, like the mirror deployment, succeeded without incident. Webb sits at the second Lagrange point of the Earth-Sun system, a location 1.5 million kilometers from Earth in the direction away from the Sun. At this point, the gravitational pull of the Sun and Earth combine to keep the telescope in a stable orbit around the Sun that matches Earth's orbital period. The telescope always faces away from the Sun, Earth, and Moon, keeping its cold side permanently shaded and its field of view permanently available for observation. The telescope launched on Christmas Day, 2021, aboard an Ariane 5 rocket from the Guyana Space Center in French Guiana. It reached its operating position about a month later. First light images were released in July of 2022, confirming that all systems were functioning correctly and that the telescope's resolution and sensitivity matched or exceeded design specifications. Since then, observations have been proceeding nearly continuously, interrupted only by occasional maintenance operations and by the time required to transmit accumulated data to Earth. The scientific programs are allocated through a competitive proposal process. Astronomers worldwide submit proposals describing what they want to observe and why. An international committee reviews the proposals and allocates telescope time based on scientific merit and the uniqueness of what Webb can contribute compared to other facilities. Time on Webb is the most precious astronomical resource currently in existence. Every hour of lost observing time represents science that cannot be recovered. Webb is a joint project of NASA, the European Space Agency, and the Canadian Space Agency. The mirror, spacecraft structure, and communication systems were built primarily by Northrop Grumman. The instruments were developed by international consortia involving dozens of research institutions across North America and Europe. The mission is operated by the Space Telescope Science Institute in Baltimore, Maryland, the same institution that operates the Hubble Space Telescope. This institutional complexity reflects a truth about modern astronomy. The questions being asked are large enough that no single nation or institution can address them alone. The scientific community that interprets Webb's data is global. Papers describing results have authors from dozens of countries. The data itself is made publicly available within a year of collection, ensuring that any researcher anywhere can contribute to the analysis. This openness is not universal in science, but it is a characteristic of modern astronomy, and it has demonstrably accelerated discovery. Multiple independent teams can analyze the same data, identify different patterns, challenge each other's interpretations, and collectively arrive at a more robust understanding than any single team could achieve. The 797,000 galaxy catalog from the Cosmos Webb field was released publicly, along with interactive tools allowing anyone with an internet connection to browse the data, zoom into individual galaxies, and access the measured properties of any object in the catalog. Researchers at universities without significant observational resources can contribute to the scientific analysis of the most powerful space telescope ever built simply by downloading the data. This democratization of observational data represents a genuine change in how astronomy operates. For most of the history of the field, access to large telescopes was restricted to small groups of astronomers at institutions that owned or had formal access to those facilities. The shift to public data releases, driven partly by funding agency requirements and partly by cultural change within the field, has broadened the base of researchers who can contribute to frontier science. Analysis tools developed at one institution are shared freely and used by teams around the world. Software pipelines that reduce raw detector output into calibrated images and spectra are maintained as community resources. The scientific output from Webb reflects this community structure. Thousands of papers have been published using Webb data in its first 2 years of operation. The breadth of topics covered is striking. Galaxies in the early universe, star formation in nearby molecular clouds, the atmospheres of exoplanets, the surfaces of solar system bodies, the stellar populations of local group dwarf galaxies, the accretion disks of active galactic nuclei. Webb is contributing to almost every subfield of astronomy and planetary science, not because it was designed to address all of them, but because it collects infrared light exceptionally well, and infrared light is relevant to almost everything astronomers study. The exoplanet results deserve particular mention in the context of this broader story about cosmic scale and what the universe contains. Webb has analyzed the atmospheres of multiple exoplanets by observing them as they transit, passing in front of their host stars from Earth's perspective. During a transit, starlight filters through the planet's atmosphere, and different atmospheric molecules absorb different wavelengths. The resulting spectral signature reveals which molecules are present. Webb's detection of carbon dioxide in the atmosphere of the hot Jupiter WASP-39b was the first direct detection of this molecule in an exoplanet atmosphere, establishing that Webb could do exactly what atmospheric scientists had hoped. More significantly, for questions about habitability, Webb is analyzing the atmospheres of smaller, potentially rocky planets. The TRAPPIST-1 system, orbiting a dim red dwarf star 40 light-years away, contains 7 planets, 3 of which orbit in the region where liquid water could theoretically exist on their surfaces. Whether these planets actually have atmospheres, and if so, what those atmospheres contain, is directly relevant to whether they could support life. Webb is the first telescope capable of characterizing the atmospheres of planets this small around stars this faint. Early results from TRAPPIST-1 observations have been mixed. Some of the planets appear to lack substantial atmospheres based on the absence of expected thermal emission features. Others remain inconclusive. The detection of a genuine biosignature, a chemical compound in a planetary atmosphere that requires a biological explanation, would be one of the most significant discoveries in human history. Webb is not yet at the sensitivity required to definitively detect or rule out biosignatures on Earth-sized planets, but it has established that such characterization is possible in principle, and has set the stage for future, more sensitive missions to follow. The direct connection between Webb's exoplanet research and its deep field observations is through the question of cosmic context. We now know that the universe is far more abundantly populated with galaxies, stars, and therefore planets than previous surveys indicated. We know that the chemical enrichment that makes rocky planet formation and complex chemistry possible was proceeding in the early universe earlier and more rapidly than expected. We know that the conditions needed for stars like our Sun to form from enriched interstellar gas were present in many galaxies for most of cosmic history. The universe has been in the business of making potential homes for chemistry and biology for a very long time and in very large numbers. Whether any of those potential homes have actually produced life, and whether any have produced life capable of asking these questions, is unknown. The Fermi paradox, the observation that a universe this old and this large should have produced observable evidence of advanced civilizations if they exist, but we see none, remains unresolved. Its resolution might involve the rarity of life, the rarity of intelligence, the short lifespans of technological civilizations, the inaccessibility of interstellar distances even to advanced technology, or the possibility that signatures of other civilizations exist, but we have not yet looked in the right way. Webb is not searching for extraterrestrial intelligence. That is not its purpose or its capability, but it is providing the most detailed picture ever assembled of how common the conditions for life's emergence are in the universe, and that picture is more abundant than any previous estimate suggested. The scientific journey that Webb represents, this decades-long effort to build and deploy an instrument capable of seeing the universe's first light, reflects something important about human curiosity. Nobody building Webb knew exactly what it would find. The specific discoveries, the record-breaking galaxy distances, the population 3 stellar signatures, the too much light problem, the Einstein rings, the cosmic vine, were not predictable in advance. The argument for building the telescope was not that these specific things would be discovered, but that a sufficiently powerful and appropriately designed instrument pointed at the universe would reveal things we did not know and could not predict. This is how observational astronomy has always worked. Galileo did not know he would discover moons orbiting Jupiter when he built his telescope. Hubble did not know he would find that galaxies were receding when he measured Cepheid distances. The cosmic microwave background was discovered by Penzias and Wilson while they were troubleshooting what they thought was noise in their radio antenna. The universe consistently has more to show than the theoretical frameworks available at any given moment can predict. Webb is operating in that same tradition, designed by people who understood what kinds of observations were needed, built with extraordinary precision and care, and producing results that are simultaneously confirming some predictions and deeply challenging others. The next decade of its operation will determine which of the current surprises represent systematic revisions to cosmological models and which represent refinements within the existing framework. Both are valuable, both advance understanding, and both are only possible because the data exists to test theoretical ideas against. What we know today about the universe is vastly more than what was known when the first serious proposals for Webb were submitted in the 1990s. What we will know in 2035, after another decade of Webb observations plus contributions from other new facilities, will almost certainly be vastly more than what we know now. The universe is not running out of structure to reveal. We are not approaching the end of discovery. We are, by most measures, in one of the most productive periods of observational astronomy in history. That productivity is a consequence of having built and deployed the right instruments and having the scientific and institutional infrastructure to interpret what those instruments return. It is also a consequence of the universe itself being as large, as old, and as structurally complex as it is. A simpler universe would have offered fewer surprises. A smaller one would have provided less to observe. The specific character of our universe, its size, its age, its physical laws, its dark matter and dark energy, has produced a cosmic history rich enough that exploring it with increasingly sensitive instruments keeps returning. Discoveries that challenge and extend our understanding. We happen to be the species that built those instruments and ask those questions. Whether that is coincidence, necessity, or something else is another question that lives at the boundary of science and philosophy. What is not in question is the result, a detailed, empirically grounded picture of cosmic history spanning 13.5 billion years, assembled from light that crossed an expanding universe to reach detectors cooled to near absolute zero, floating in the darkness 1.5 million kilometers from the planet where the questions originated. There is one more aspect of what Webb has revealed that deserves careful attention: the concept of look-back time as a research tool, and why the ability to observe the universe at different epochs is fundamentally different from simply having a more powerful telescope. If the universe were static, if galaxies had always existed in the form they take today and had always been at their current distances, then more powerful telescopes would merely provide higher resolution images of a fixed distribution of objects. The scientific value would come from seeing individual stars or gas clouds within distant galaxies in sharper detail. That would be scientifically valuable, but it would not tell us how the universe changed over time. What cosmic expansion does is transform distance into time. The farther away an object is, the longer its light has been traveling, and therefore the older that light is. Observing a galaxy at a redshift of 1 means observing it as it appeared roughly 7 to 8 billion years ago. Observing a galaxy at a redshift of 6 means observing it as it appeared about 12.5 billion years ago. Observing the record-breaking objects at redshifts above 10 means observing the universe as it existed in its first few 100 million years. This means that a single deep field image contains multiple epochs of cosmic history simultaneously. Nearby galaxies appear as they are now. Intermediate distance galaxies appear as they were billions of years ago. The most distant galaxies appear as they were close to the beginning. A single exposure collects information spanning almost the entire history of the universe, layered one behind the other like geological strata, except that instead of digging downward into rock, you are looking outward into space. Webb's unique contribution is pushing the accessible epoch to within 300 million years of the Big Bang, closer to the beginning than any previous observatory. At these distances, the universe was in the process of undergoing some of its most dramatic transitions. The first stars were switching on. The first galaxies were assembling. Cosmic reionization was transforming the transparency of intergalactic space. Supermassive black holes were growing from their uncertain seeds toward the masses they would eventually reach. The chemical composition of the universe was shifting from near-primordial hydrogen and helium toward the enriched mix that would eventually make rocky planets possible. All of these processes left observational signatures that Webb can detect in the spectra and photometry of the objects it sees. But interpreting those signatures requires theoretical frameworks sophisticated enough to make precise predictions. This is where the current tensions become most scientifically important. Standard models make specific predictions about what the universe should look like at each redshift. When observations consistently depart from those predictions in the same direction, it means the theoretical framework needs revision. Revision is not failure. Every successful scientific theory is eventually superseded by a more comprehensive one that explains everything the previous theory explained, plus the new observations the previous theory could not accommodate. Newtonian gravity was not wrong within its domain of applicability. It was incomplete, unable to describe the bending of light by massive objects, the precession of Mercury's orbit, the existence of gravitational waves. General relativity superseded it by including all of these phenomena in a more comprehensive geometric framework. General relativity itself is known to be incomplete. It breaks down at the quantum scale. where a theory of quantum gravity that nobody yet has is required. The standard cosmological model, lambda CDM as it is formally called, where lambda stands for the cosmological constant describing dark energy and CDM stands for cold dark matter, is similarly successful within its domain and similarly known to be incomplete. It accurately describes the expansion history of the universe from fractions of a second after the Big Bang to the present. It accounts for the pattern of the cosmic microwave background temperature fluctuations with remarkable precision. It predicts the large-scale distribution of galaxies in reasonable agreement with observations across most of cosmic history, but it cannot explain dark matter from first principles. It cannot explain dark energy from first principles. It cannot explain why the cosmological constant has the value it does, and now it is failing to predict the abundance and brightness of early galaxies with the precision that Webb's observations demand. These are not minor peripheral issues. They are gaps in understanding of the universe's most fundamental constituents and its earliest history. Whatever revisions to the standard model prove necessary, they will have to be constrained by the observations that currently exist and by the observations that Webb will continue to provide. Theoretical physicists developing new models do not have free rein to explain one anomaly if doing so breaks agreement with other observations. A model that accounts for the excess early galaxy luminosity must also continue to match the cosmic microwave background, the large-scale structure at lower redshifts, the measured abundance of light elements, and dozens of other observational constraints. This web of constraints narrows the space of viable theories considerably and forces any successful revision to be genuinely explanatory rather than merely accommodating. This is why the anomalies Webb is revealing are so scientifically valuable. Not because they indicate the universe is incomprehensible or that physics is broken, but because they mark the boundaries of current understanding with sufficient precision to guide the construction of better theories. A precise anomaly is a gift to theoretical physics. It defines what the new theory must explain, and allows the scientific community to reject models that do not meet the standard. The coming decade will involve both continued Webb observations and sustained theoretical efforts to construct models consistent with everything Webb is finding. Computational cosmologists will run increasingly detailed simulations attempting to reproduce the observed properties of early galaxies from first principles. Particle physicists will continue searching for dark matter candidates and testing dark energy models against observational data. Theorists will develop new frameworks for the physics of the first seconds after the Big Bang that might account for different initial conditions than those standardly assumed. All of this will happen against the backdrop of an expanding dataset from Webb and other facilities. The Euclid satellite, launched in 2023 and operated by the European Space Agency, is conducting a wide-field survey of galaxy shapes and positions across large fractions of the sky, providing the statistical power needed to measure dark energy's properties in the cosmic expansion history with unprecedented precision. The Vera Rubin Observatory in Chile will conduct the legacy survey of space and time beginning in the mid-2020s, photographing the southern sky repeatedly and detecting billions of galaxies, supernovae, and variable stars. The Nancy Grace Roman Space Telescope, planned for launch in the late 2020s, will combine Hubble's resolution with a field of view 100 times larger, conducting deep surveys of areas of sky far larger than Webb can cover. Each of these facilities contributes something different. Webb provides unmatched depth and infrared sensitivity for the most distant objects. Euclid provides statistical power for dark energy measurements across large cosmic volumes. Rubin provides repeated observations for time-variable phenomena, like supernovae and variable stars. Roman provides deep, wide-field coverage, combining the advantages of Hubble resolution with Rubin-scale survey areas. Together they will produce a picture of cosmic structure and evolution more detailed than any previous astronomical generation could have imagined. The questions they are addressing are the same questions humans have asked since the first person looked up at the night sky and wondered what was out there and how it came to be. The answers are taking shape in the form of precise measurements, theoretical models, and the productive tension between them. The process is ongoing. The story is not finished. What we know today, thanks in no small part to Webb, is that the universe is stranger, larger, older, more chemically rich and more structurally complex than any model proposed before the telescope launched could fully describe. We know this with precision and with confidence, because it is written in the light of galaxies that formed when the cosmos was only a few % of its current age, carried across expanding space for 13 billion years, and recorded by instruments that humanity built, launched, deployed, and directed toward the most ancient darkness it could find. The universe revealed itself because we asked it to,